So this book is from, I think, 2008, which is kind of old, but it is the Bible of this field. It is one of the big standards, and there's nothing to compare with it. So I do have some additional lectures and projects to address the topics that came up after this book, the most important one being 64-bit systems. Yeah?
The book is hard to read, Sam.
It is. But it is different. It's an important topic. That's right. So I'm hoping that between the book and the projects and the lecture, you can get some of it. But assembly language is intrinsically difficult. It would be better if you went and took the assembly language course first, which is an option. But I didn't make it a prerequisite. I thought about it. But when I was first writing the course, there wasn't a good assembly language course here. There is now. There's a good assembly language course here. So if you take that even concurrently, it would make this course easier. I don't know what the name of it is, but there's an assembly language course over in CS. And I think Greg Boyd teaches it. I think it's very good. So you really learn assembly language. It's not x86 assembly language. I think it's MIPS, but that doesn't really matter. You learn assembly language. So if you, that's the most common problem is assembly language, which is kind of alien to people. And before taking a course over there, a good thing to know if you're going to do reverse engineering. But you don't really need to be very good at assembly language to do what we're doing here. The point here of this is developing exploits. If you have a server with a vulnerability where you can somehow send in input that is misunderstood by the server, the simplest attack is a denial of service attack, where you send in something that just causes the server to crash. And that is something. It's important, and they patch those, but it's not considered as useful as a remote control exploit. So the activity called exploit development is taking a denial of service attack and converting it into a remote code execution attack. So for example, buffer overflows are very simple. If you can only take 1,000 characters and I send in 2,000 characters, the thing will crash. But if I send in 2,000 very carefully chosen characters, I can make it not crash, but give me control of the server. And that's the point of this class. You'll learn how that process works, and you'll learn what defenses have been put in place to protect servers and how to overcome those defenses. And there's an endless arms race. Microsoft Windows has become very secure. For the last 4 or 5 years now, it has been very common that if you had Windows, you would be much safer than if you had Linux. It used to be the opposite, but Microsoft reformed starting in 2002. They tried to improve their security, and one of the big steps forward for Microsoft is the Blue Hat contest. They have a special convention called Blue Hat something, where they invite hackers. And they go to this conference, and if you find a way to hack into Windows, they will pay you $100,000. And if you write the defense that stops it, they will pay you another $100,000. And this has been very effective at moving Windows security up fast. And they have a lot of very clever mitigations, which we'll be talking about as we go ahead. But Microsoft is very serious about protecting their servers and their users. They don't always succeed, of course. Everybody gets hacked. But Windows has a lot of defenses, and they're very smart defenses. And Linux has had a lot of huge security disasters in the last 2 or 3 years that have really humiliated them and taken the wind out of their sails. And I haven't heard anybody in years try to say Linux is intrinsically more secure than Windows. The fact is both of them are complicated, and you have to be very careful to make them safe. Anyway, so we'll talk about a little bit of assembly code and a little bit of C here. You don't really have to know much C programming or much assembly, but you need to know a little bit so you can understand what you're looking at when you look at machine code that's running, compiled code. And then we'll talk about how to write shellcode and take over various systems. All right, there's the book. Classes are going the same way my classes always have, but now the quizzes are online and open book. You have to complete the quiz before the class covering that topic to try to encourage people to study the book first, because you really will have to go over this material more than once. So nothing's due until the 4th week of class, so that I don't have things due before people even added and stuff. And then there's 2 quizzes due per week for a while to catch up. But the point is, I want the whole class to be like this, where you finish this quiz before class, and it's due a half hour before class. You do it online, and then we have the lecture about it. So people that are in the lecture have already made one attempt to go through the material. All right, I've got the policy here, the usual thing for grading and such. So there's the textbook. There's a bunch of quizzes and projects and a final exam, so that adds up to a bunch of points. 90%'s an A, 80%'s a B, and so on. You can take it pass, no pass if you want to, but that is not good if you want to get a City College A degree or a certificate in computer security or anything. It would only be for people who are taking this class and they're really main focus is biology or something. So it's not probably much use for you to do that, but it is allowed if you fill out a form at registration within the first 3 or 4 weeks of class. So you can take the quizzes online. They'll be online for at least a week before class. You can take them anytime. You're open book because I have no way to stop you from opening the book and Google and everything while you're taking the quiz. I just want you to go over the material. Getting someone else to take the quiz for you or asking a human what to do, I would regard that as cheating, but obviously I have no way to catch you. So the quizzes will be less accurate than they were when they were in class, but hopefully they'll encourage people to read the book, which will hopefully improve their learning. If you are sick or something, can't take a quiz, let me know and I'll fill in that quiz with your final exam score. If you miss the quizzes or do badly on the quizzes, you can fix that by doing well on the final exam. The quiz score will be raised to equal your final exam score. And the final exam is not open book and it's on paper. And it happens here so I can see that people aren't like calling up somebody else to give them the answers on that. So there's a lot of hands-on projects, and that's what most people see as the main focus of the class, learning how to really do something. And so you got to turn in a lot of screenshots for that. So you have to have the prerequisites here. You should know basic networking and basic security, and it would not hurt if you know some C or some assembly, but if you don't know any, we will go over it, the little bit we're using. And you of course have to have a computer and the textbook and time to do the projects and study the book. If this class is too hard, you can go back and take earlier classes. We have a whole program of earlier classes to prepare you, so you know, that's fine. That's why you have the first 3 or 4 weeks to add and drop classes. If this isn't right, go back and take 106 or 120 or something else. You're learning how to attack machines, so obviously you can commit crimes and go to jail, so don't do that. These techniques can only be used on test systems like virtual machines you're set up to attack, or on systems that have been set up, like my servers, are set up deliberately to be attacked. Things where you have permission to attack the server. These techniques will work on other people's servers, but it's a crime, and I can't save you if you do that. If people are cheating, turning in other people's homework with their own name on it and stuff like that, I generally throw them out of my classes. Because if you're going to be a security professional, you're going to be like a cop or security guard. You have the ability to go anywhere on the system. You can read other people's personal data, and you just have to have enough integrity to not do that. So if you don't even have enough integrity not to cheat in a college class, it is for your own protection that you should not get this job. This is like handing a gun to a toddler. So you'll end up in much bigger trouble if you go on the job and start doing unethical things. So you don't get points for attending class, you don't lose points for missing class. All the points come from quizzes and projects, and the quizzes are now online. But hopefully the class will be valuable enough that it's worth coming in. But if you do miss a class, you can look at these videos. And does anybody have any questions about anything? That's all the usual stuff. All right, so let me pardon me, move on to the first chapter, which is here. And there it is. Good. Oh, that's the wrong one. That's the old one from last semester. And now I've converted them to keynotes and made some updates. There wasn't a lot of updated needed, but I updated it somewhat. All right. So here's some basic concepts. You can only take over something if it has a vulnerability. There has to be some kind of flaw in the thing you're attacking. Like I say, the simplest thing is a denial of service vulnerability where there is some way to make it crash. There may be privilege escalation vulnerabilities that let you increase your rights to do something, like from a limited user to administrator. And the most common thing people go for is remote code execution, where you can pass up any command you want, it'll be executed on the server, then you really own that server. So exploiting is the process of taking over a server, doing something unexpected, and a 0-day is an exploit that no one knows about yet. So nobody can defend themselves. There's no antivirus definition for it. People don't know they should be watching for it. And these things are expensive, difficult to create, and worth a lot of money. If you find a vulnerability in iOS to take over an iPhone, it is worth $1 million right now. And these things are sold. You almost never see them released publicly anymore because they're worth so much money. They are sold to military organizations like the NSA and other countries largely. A fuzzer is a way to find a new vulnerability. There are basically 2 ways to find vulnerabilities. One is to read the code and look for patterns of code that indicate the flaw, and that works for open source projects or for projects at your company where you have the source code. But if you don't have the source code, the alternative is a black box attack where you just send random data to the process hoping it will crash. And when it crashes, then you try to catch that crash in a debugger and analyze it and decide if you can do more than just crash it. Most vulnerabilities can only be used to crash the server. Only a small percentage of those have a way where you can actually control it and take over the server. All right. Now we're going to talk, the memory corruption is pretty much what we're going to be doing here. It's the most common type of vulnerability. This is mostly what you do, where somehow you cause some data to overflow the area it's supposed to be in and overwrite other data. That's typically how you take over a server. You can do it in the stack or the heap. And sometimes, anyway, that's the point. So you have to understand how memory is used by a normal process. So then you can understand how that can go wrong and give you control of the server. Computers are very strange things. All you have is a series of bytes. The computer doesn't know what they mean. Your instructions that do commands are just a series of bytes. Your images are just a series of bytes. Your videos and everything are just a series of bytes. It's a strange thing, and that's what makes system exploitation possible. You confuse the computer about how to interpret something. One simple example was the GIFR vulnerability. It turns out that a GIF has a header but not a footer, and a jar, which is a Java executable, has a footer but not a header. I might have those backwards, but the point is you can make a file that has a GIF header and a jar footer. If you end the file name with .gif, it will interpret it as an image and display the image. If you end the same file with a name ending in JAR, it will interpret it as Java executable code and execute it. This was a big exploit about 5 years ago. It won a pony at DEF CON because you could take any site that would let you upload an image, like to put it in your profile, and you could upload Java code and then trick it into misinterpreting and running the code. So it gave you the ability to execute code in a system that thought you were just sending up images, which is cool. And that's how all these attacks work. You somehow confuse the computer into executing stuff that was not originally intended to be code. All right, so every time you run a program, it has its own address space. Sort of like a virtual machine, all Windows programs think they're running at the same memory address, which is 400,000 in hex. They have a base address that the program doesn't know about, and they all think they're running in the same addresses. So there are a lot of segments of memory, but the three that you always find are these: text, data, and BSS. Text contains the instructions. And in modern code, this area is not writable. Now, when I wrote assembly language starting long, long ago in the world of 8 bits, I wrote self-modifying code all the time because it was the way to get things done. But self-modifying code is sort of horrible, where you have a series of instructions and the instructions overwrite the instructions and cause it to do something else. You can't even write it down or make a flow chart. And they made it impossible on modern computers because it is such a poor practice. So the text is the instructions. Then you have data down here for static variables, and then you have uninitialized global variables, which are the variables that change while the program is running. The stack is the most common place you attack. It is easier and simpler to perform stack overflows than heap overflows, but we will do them both. But historically, this was a black hat technique used in rumors until I think 15 or 20 years ago. Aleph Noel wrote the original FRAC article exploiting the stack for fun and profit that explained in very simple, clear terms how to do a stack overflow, and that started everybody understanding exploit development. Before that, it was a rare, concealed skill. And that's what we're going to do here. We're going to start on the same historical trajectory. A simple stack overflow is the first thing to understand. All the later attacks are variations on that. The original stack overflow doesn't work on a modern operating system most of the time because they put in defenses because everybody's been using it for so long, but it is the right way to learn it. So the stack is a special area of memory designed to make it possible to have structured code. Now, when I started long, long ago, I programmed Fortran 4, and we mostly wrote just spaghetti code. Although in principle it could be used for something better, we just have a bunch of code and then go to and jump down here and then go to and jump up here, and the actual flow would be running back and forth like a lunatic. And it was very hard to expand or modify that code. What's much better is to organize your code like modern C programs. So you have, you'll have a main routine, and instead of having many instructions here that do something, you'll just call a subroutine that does something and then returns. And then you call another subroutine that does something and then returns. So whatever your task is, you break it up into little chunks. And you write one subroutine here that does one thing and you call it. Then you write a subroutine here that does one thing and call it. So you can have a bunch of developers working each on one little piece of it and getting their piece right, and this just calls them. So the fundamental flow of a modern program is that you're in one environment, like the main routine, and you have to jump into another environment. You have to remember where you left off. So I was at this instruction, I'm going to resume at this instruction, so I jump down into this routine, I have to execute all this stuff, and then hit a return at the end. And when I hit the return, it has to jump back up here and pick up where it left off. So it has to remember somewhere where to pick up. And the basic trick is I managed to change that value so it gets confused about where to return to. And instead of returning to the next instruction, it returns somewhere else that's under my control, like down here, where I've injected stuff, which now runs. That's the trick. And so the most common kind of overflow, you're trying to gain control of the extended instruction pointer, which is the pointer in the process that tells it which instruction you're working on. And then you have a chance to take over the machine. So the heap is the other main data structure used that changes during execution. The stack is carefully designed to make this efficient, where you jump into a subroutine and that might jump into another subroutine and another subroutine, and you might have many of these, many layers deep, and the stack is designed just to make that process work well. But the other process, where you might have a temporary storage of things, like you're listening on a network socket and in come a bunch of packets, and you can't really process them all right away, so you want to store like 10 kilobytes of data for later processing, and after you're done processing it, you want to let go of those 10 kilobytes and make them available again. That's what the heap is for. I need some space, I'm going to use it now, then later on I'm done with it, I'll give it back. All right, so here's what it looks like in RAM, a simplified diagram of a Windows machine running. You've got kernel space, which is the fundamental heart of the operating system. The kernel is the only part of the operating system that can directly talk to the hardware. If you're writing a program in C or something and you want to send a network traffic out, you call some kind of socket library saying, please open a TCP socket, send out some data. You do not get to send any signals to the network card. You ask the kernel routine, please send this out the network card. And the kernel routine and the device driver that live in kernel space do it. You are not authorized to touch the hardware. You're like the executive sitting on the top floor of a building and you want to mail something, you're not allowed to mail it, you don't know where the stamps are. All you can do is ask the mailroom to please send this for you, and they'll do it either right or wrong, but you are not authorized to touch that stuff yourself. All right, so here's the stack. The stack grows down as you descend deeper and deeper into subroutines. It puts frame after frame here to remember what it was doing when it's time to come back. Then there's memory mapping here, and the heap grows up. And then there's the other segments down here. And way down at the bottom is the text segment that contains the machine language instructions that are running all this. So I got a few iClicker questions about this stuff. If you, so turn on your clicker at the bottom. Let me see if my app is going to work. If you didn't get one, come grab one. And there's the app. Let's see if it's going to work. All right, let's get rid of this. I'm just going to start this thing. And go ahead and hit a button. Just see it, just see everybody going. You got 11 people that have got it working. So you can keep changing your vote until I stop the clock, and then the last vote counts. So looks like 17 people have got it going. I guess that's enough. That's the game here. And if you get the most iClickers right, you get 3 points at the end of each lecture. So there is some value in this, but the main purpose is just to keep people from falling asleep. So, all right. So, what is an attack with no known defense called? And this thing, it should be listening, but there now it's listening. All right. Make that bigger if I can. There we go. All right. All right. Looks like I can quit at 25 seconds. Only 15? Maybe that's right. I don't know. Anyway. All right. So, that's a 0 day. You rate exploits by how many days it's been since the patch came out, or since the information came out that warned people, and a 0 day is one where the information has not come out at all yet. So even if you're reading the journals and blogs and talking to the experts, you will not see this coming. All right. Which one is a weakness? looks like 25 will do. All right, and the weaknesses of vulnerability, of course. Good, everyone knows that. Glad to see it. All right. Come on, knock it off. All right. So he sends random data to a target. What's that? All right, I'm quitting at 25 again. All right, and that's fuzzing. Good, good. All right. Which part is LIFO? Which is last in, first out? I'm quitting at 25. All right, and that's the stack. This is one of the strange things about the stack. If I'm in the main routine and I jump to a subroutine and then I jump to another subroutine, I want the last information I put in to be the first to come out when I jump back up. If I go down A, B, C, I come back C, B, A. So the stuff I put in should come out in reverse order. And that's how the stack is designed. All right. So, good, all right. And where are the machine language instructions? Tell the processor what to do. I'll quit at 25. All right. They are in the text section, which is kind of screwy. I don't know why they use text for commands, but that's what they call it. All right. And so which part is read-only? I quit at 25, and I might have a problem with this one.
You know already.
All right, the text section is read-only because you're not allowed to write self-modifying code, but I'm afraid the data section is also read-only. Let's go back up here.
Wait, miss, back up, right? No, one more.
Someplace up here. There.
There it is.
Yep, the data is writable. Okay. It is writable, this is writable, but that's not. They're initialized when the program starts. Anyway, so I think I'll settle for text as an acceptable good answer for that one. All right. But you could argue about the data section. All right. So let's talk about this assembly code. The assembly language is intended to be human readable. Now the machine language is just binary. That's what the machine uses. Now that is really hard for humans to read. So assembly language is trying to convert the binary machine language into something that looks a little bit like English. It's still pretty hard to read. And that's why reverse engineers are considered very skilled, people who can really read assembly and work in it. That makes you LEET. That's the classic LEETness. That's a goal to strive towards. We're going to get a little bit of that knowledge here, but we're not going to be experts in assembly by any means. Yeah?
What are AMD processors? What would they be?
AMD, they're x86 and x64 compatible. They're Intel compatible.
Oh, okay.
Yeah. So the most common, of course, for PCs is 32-bit Intel, although now 64-bit Intel is quite popular too. And on portable devices, you have these other things like ARM and so on. Your machine language depends on the processor, and therefore your assembly language depends on the processor. All right. Most malware is designed for 32-bit Windows because it'll run on 32-bit or 64-bit Windows. In the last 4 or 5 years, I've heard a few examples of native 64-bit malware, but it's not very popular because there's no real reason to bother. 32-bit malware is typically just as effective. Yeah.
Would you say that 64-bit malware may be a little bit better for evading AV?
Not in principle, but it's possible that there'll be a period of time when the AV people haven't updated or something. But anything new will be surprise at first, but I don't think it's new anymore. Yeah.
64 bits just for addressing memory anyway, right? It doesn't
The
really
instructions
give you
are
an
different.
advantage unless you're gonna
No,
do
well,
something.
the only advantage is it should run faster on a 64-bit processor, but if you do write it, it can't infect 32-bit machines. So as long as there's a lot of 32-bit machines out there, there's a financial incentive not to do it. But now even the iPhone is 64-bit, so 32-bit is on the way out, except for the Internet of Things. Those little gadgets do everything crappy to make them small, and but exploiting those, you don't even need exploit development. They typically have hard-coded default passwords and stupid things like that. Which reminds me, by the way, if you go to my website, I put this here. You might want to check this out. A student contacted me. There's a Federal Trade Commission Internet of Things contest, and you can win money by doing this. This is actually pretty brilliant. Because of the Mirai botnet, which has been creating havoc for the last 2 or 3 months, a Chinese manufacturer made these webcams that many people bought that just have a default password. And either you can't change it or nobody bothers, but there's millions of them out there with the default password. And so people are just taking them over and using them for attacks. Then somebody else takes them over and uses them for attacks. The Internet of Things is just like a million army soldier for anybody to use to do any harm they want. And this is going to get much worse before it gets better, as everybody's light bulbs and thermostats and refrigerators and everything are on the internet, all built very poorly with no security in mind. So the FTC contest is to build a device to secure home users. Some extra firewall or router-like thing that will help fix this problem, assuming, which is going to be the normal house, that your house is full of dozens of things on the internet that you don't even know about or understand, all designed poorly. That's going to be the average house of the future, like next year. And they said, if you will build some kind of box that will secure this house, they'll give you a prize, because you can't expect the manufacturers to update them all and the home users to figure out how to put the patch on everything. But what they could do is buy some kind of gadget, stick in there to protect me. And so if you can make one that actually works, they would like you to. Yeah.
Doesn't this really fall on the carriers to fix this problem?
You can try that, but the fact is, in America, this has been a big argument. In Australia, if you infect your home PC and you start attacking people, your internet service provider will pop up a message on your screen and say, dude, clean your box, and if you don't do it in 30 days, they'll pull the plug, because they're forced to by the government. But in America, they are not. So they can see that you're infected with malware and attacking people, but they continue to make money by charging you every month for the service, and they aren't required to do anything about it, so they don't. So you could pass a law forcing carriers to block this stuff. That's one option. You could force a law forcing Internet of Things people to go through some kind of test and improve their stuff, but all that is like 10 years out. For the next 10 years, we need something like this to limp through the transition period.
The D-Link currently has a suit against them.
Yes, D-Link is finally being sued for making a router that was so terrible that it was considered substandard enough that you can get sued, and a couple of people have been sued for their apps being too rotten, Fandango and Credit Karma, but there's only been like 3 or 4 major lawsuits here. When there are like more major lawsuits or people actually die or something, then it will start a scandal, and then about 3 years after that, the committees will start meeting and a law will eventually come out, but realistically, that's 10 years out. For the next decade, we need this thing. Anyway, it's a cute idea, and some students are talking about forming a team to build this gadget. They say, whatever you figure out, build it, and let's see it, and whoever built the best one, or the second or third runners up, will get some prizes, as well as eternal glory. And by the way, obviously, you could start a company making that thing and selling it. Anyway, it's an interesting puzzle, and worth looking into. All right, so the machine language instructions, assembly language instructions look like this. You have a mnemonic followed by operands. So move is the command to move data from one place to another. The operands here are ECX and 0x42. ECX is a register. There are about 12 registers in the x86, and you'll get to know and love them. Originally, when I started this, there was an 8-bit processor, and there was one register called A, because it was the accumulator. And this was from mechanical adding machines from 1930, where you'd type in numbers and go chunk, and type in numbers and go chunk, and the wheels would turn and you saw the total. That's the accumulator that accumulates all the numbers that come in. Then they moved to 16-bit and had AX, I think the extended one, and then they moved to 32-bit and had EAX, the extended A extended. So There's now 4 main registers for general purpose: EAX, B, C, and DX. But there's other registers too. So what this command does is it takes the literal number 42 and puts it in register ECX, which is a little bit of memory on the processor. It's not part of main memory. So in your like 4 or 8 gigabytes or however much memory you have, there's a little bit of memory on the processor, and those are the registers. Intended to be used for temporary storage of things, and when you're done figuring things out, then you write it to main memory, where it can go places like the video card and the network card and such. So 0x just means it's hexadecimal. Everything is typically written in hexadecimal. This is not 42, it's 4 times 16 plus 2, so that's 66. Anyway,
Wait, what?
4 times 16 plus 2, it's hexadecimal. So the left is the number of 16s and the right is the number of 1s. And the biggest number is FF, which is 255. So in binary, this is what this instruction looks like. B9 is the binary for move. And then here's the 42. And B9 is actually the hex for move into ECX. So this string of binary is the machine language. That is the human readable assembly language. Like I say, it's not very human readable, but it's a little better than you're trying to read this. All right. So now, unfortunately, there's big endian and little endian both in use just to give us all headaches. So if you have a number that's 42, but you have a 32-bit processor, it has to have 4 bytes for every word. So now the way you would write it in like the normal way you write numbers should be this way: the big thing's on the left, so it's all zeros, and 42 on the right. And that's called big endian, where the big numbers come first. Little endian, you write it this way, backwards. So this is the number of 1s, this is the number of 256s, this is the number of 65,000s, and that's the number of, I think, 17 millions. It's in base 256, if you want to look at it that way. Anyway, unfortunately, network data comes out big endian, and the programs store other data in little endian. So you sort of get frustrated. It takes a little practice to see which way things are going to be. And this is how things get backwards so many times. And parenthetically, this is why there are bad neighborhoods on the internet. A couple of years ago, we ran out of IP version 4 addresses. And they sold the last few rotten parts of IP version 4. They were distributed to companies. Not sold, but given by Aaron. And one of them was the 1 block. There's a perfectly valid use of a bunch of IP addresses starting 1, like 1, 2, 3, 4. That's a public IP address that you can put a server there, but no one wanted this block. They didn't get it until all the others were gone, because this block is a mess. There is a ton of traffic on the internet going to this address, and one of them is there's a whole generation of telephones, IP phones, that are constantly sending busy signals to 1.1.168.192 because they got the address backwards and they're sending traffic constantly here. So if you buy the 1 block, you will find out all this traffic flooding into your network that is garbage. So that's a lot of people get confused for big endian and little endian, and things come out backwards. Anyway, so that's the game in hex. 127.0.0.1 would be that way, and it's sent over the network with 7F first, but if you store it in RAM as a variable, it's stored the other way. So that's one thing to be aware of. So immediate values are fixed numbers, like 1 and 2 and 42. Those are just plain numbers. Registers are these little memory locations on the processor, like EAX, EBX, and ECX. And then you got RAM. And RAM you refer to this way. You put brackets around it, and then the number in there, and that points to the location in RAM. So you can take EAX, which includes a 32-bit value, and if you put it in brackets, it will refer to the memory location pointed to by EAX. So here's the registers: EAX, EBX, ECX, and EDX. Then the extended base pointer, the extended stack pointer, and the extended indexing, ESI, eFlags, and EIP. The most important of all for us is EIP. EIP is the counter that says which instruction to execute next, and most of the time, the way you take over the box is by controlling EIP to make it jump and run code that the developer did not intend for it to run. All right, so that's the general registers, and there's segment registers. Like I said, the most important thing for us is usually the EIP. They're all 32 bits in size on a 32-bit machine, and that's what we're mostly going to talk about in this class. We will talk a little bit about 64-bit later, but 32 is the main thing to understand here.
What
And
did you say was ESI?
ESI is like an index counter used to count through arrays and stuff, a general purpose. It's used, I think it's extended something index. I forget what the S is for. Might be stack index, I'm not sure. The EBP is typically the base of the stack, and ESP is typically the top of the stack. But they can all be used for any purpose in principle. But usually that's what they're used for. So they're all 32 bits. In case you actually want an 8 or 16-bit value, the A, B, C, and D registers can actually be broken up into chunks. A low and A high is 8 bits. And you can refer to 16-bit portions of it also. This is not very commonly done. This is in case you actually want to run like 8-bit code, which is not much of it anymore. But in principle, you can refer to smaller registers, and occasionally people do this, but it's not terribly common. All right, so general registers can store anything. It's usually data or addresses. Sometimes there are specific purposes. When I started, there were no multiplication or division instructions. If you wanted multiplication, you had to write algorithms to do adds. If you wanted division, it was actually pretty frustrating and complicated. Now they actually include multiplication and division operations, and they use EAX and EDX. But we're not going to worry about that for anything we're doing here. We're only interested in more simple things. Most code is not written in assembly language. It is very expensive to write assembly language. A human has to work really hard to accomplish very little. Most people like to write in a high-level language like C or Python or something. And if you write in C, you then run it through a compiler, and the compiler creates the machine code, and therefore the assembly language. So the compilers actually choose to use certain instructions. Now, there was a time long ago, before Apple used x86, they used Motorola, and Apple was the champion of RISC, where they would have a reduced instruction set. The processor only had a small list of instructions, and it tried to make them fast. Intel was the opposite. There are 10,000 instructions in the Intel processor because there's every possible variation. They're really boring. There's only like 8 things you can do, like move and jump and compare, but you can move from register to register, move from register to memory, move from register to memory plus a register, just minor variations. And it turns out that nobody uses them. The people that write compilers only use like 10% of them, and that's all that's ever actually used. All the rest are worthless appendices. But anyway, the compilers have conventions. E-flags has a bunch of individual bits that indicate things like whether the last operation resulted in 0 or not. And that's what you use to do things like comparisons, to compare two things and see if they're equal. So Z is set if the last thing resulted in 0, and there's a few others I'm not going to worry too much about here. So the EIP I mentioned is the most important thing. This is which instruction you're executing. So normally you execute one instruction, then you move EIP forward a few bytes to the next instruction, and the next, and it just counts through your program. But if you call a subroutine, it jumps from here way to somewhere else, and it has to remember how to come back, and that's the point of vulnerability where we're going to take over the machine. All right. So I got a few questions here, and then I think we'll take a break. All right. So,
Oh, one question.
yeah,
Before you go.
yeah, go ahead.
In one of the slides you said the braces around a register means something. What does it mean?
The square brace, those mean it is an indirect address. So if I write EAX, that means I'm referring to what goes in that location. If I do this, then I'm going to interpret those 32 bits as an address and write to that part of memory.
Pointer.
It's a pointer then, yes. So the square brackets mean you write to this RAM location. Without the square brackets, you're referring to either immediate values or registers.
And another slide you pointed out the network data 127.0.0.1.
Yeah.
It 7F001. And it's sent out just like that, right? 7F001.
Yes, it's sent out with the high order first, but it's stored as a variable at the high order last. So it can be confusing. And that's why people end up with mistakes like this. Good. Any other questions? Okay. Try a few of these then. So what kind of assembly language is malware written in? I've been waiting. Well, I don't even know when I started. Looks like I can quit. Anyway, so it's written x86, which is 32 bits.
ARM has to be getting a lot more popular with mobile phones.
What's that?
ARM has to be getting a lot more popular with the mobile phone.
It might be, but there really aren't that many mobile phone viruses. There are 100 million Windows viruses, there are 1 million Android viruses, and there are 100 Mac viruses. And there are 0 iOS viruses. So your safest computing platform is the iPhone. And Android is one of the first giant demonstrations that if you really try hard enough, you can make Linux just as bad as Windows ever was for security. All right. So, the loopback address is that. What kind of notation is that in? All right, I'll quit at 25. Looks like the answers are in. All right, that is big endian. The big number is first, the 127 is first. And then the 001 is over on the right. This is the normal way you'd write it. The big number here, the small number there. All right. Move and an XOR. What are those things? All right, I'm quitting at 25. All right, that's called a mnemonic. That's the part that's human readable. The alphabetic part. The operands are the things after it, like names of registers and locations. The mnemonic is the human readable term that tells you what the instruction does. You might also call it a verb, but they call it a mnemonic just to give us all headaches. All right. So an instruction puts data in EAX. What type of operand is EAX? I'll quit at 25. All right, that is a register. Good, a popular answer. All right. And how about this one? AX with brackets around it. What's that? Oh, I'm quitting at 25. All right, that's a memory address. It's referring to a location in RAM. There, good, all right. In C, they call these things pointers or indirect addressing. There it goes. All right. So, we've been here for an hour, and we got a bit more I'd like to do. Let's take a 10-minute break. And who came here to add? Just one person? All right. Well, let's do that. Let's pick up at like 15 minutes after 7. Stop the recording. I don't know. Not a whole lot longer, I reckon. This is going to be 127, chapter 1A.